Okay, so topic for today is kinematics, which basically deals with the study of motion of objects traveling in straight line. Okay, so whenever we are referring to straight line motion, we can probably consider the fact that we are studying kinematics. Now, when we refer to straight line motion, it could be in two perspectives. The motion could be horizontal, okay, due to some external force. Likewise, it can be vertical as well. So not just vertically downwards, it could also be vertically upwards. Likewise, it can be horizontally to the left as well. So when we study these motions independently, that the study of that is said to be kinematics. So like we discussed in our initial discussion based session, there are some prerequisites that the curriculum expects. So knowing the differences between distance and displacement. Okay. So primarily distance is a scalar quantity, displacement is a vector quantity, which means we need to specify magnitude as well as direction to give complete information about displacement. Likewise, for distance, we just need to give the magnitude. Now, there's another thing along with magnitude that we need to indicate, that is unit. So it's always magnitude plus unit and direction. Okay. So this takes us to the next part of the context to understand that when we're referring to terms like distance, displacement, and we will also be talking about speed, velocity, and so on. So there are some units also associated with those. Okay. Now there is a concept of measurement and units apparently that has been taught in the curriculum. Now that element is not explicitly assessed in paper one or paper two, but there are questions based on uncertainties and units, which are going to be part of experiment-based questions. So as we go on with the sessions ahead, we will try doing some experiment even in the virtual scenario, and then we will try to understand that concept as well. Okay. So relating to distance and displacement, we are all aware of how to calculate it. Okay, so we are not going to really overspend time doing this right now. Okay, we are going to straight away move to the concept of speed. Okay, now when we're referring to speed, there is a possibility that I may travel from A to B, I may travel from B to C, and then C to D. And here I might just take 5 hours, here I might take 1 hour, and here I might take 10 hours to travel. Whereas the distance was always the same, 10 kilometers, 10 kilometers, and 10 kilometers. Now there could be many factors due to which why I did not travel at a constant speed. Okay. Maybe traffic, maybe I stopped by to eat something. Between B to C, I did not stop, I traveled the fastest. But if I want to calculate what was my average speed, okay, for the entire journey. So then we need to know the total distance traveled, that is from A to D, okay, over the total time taken. So when we are referring to speed in our context, we are going to be referring speed in two ways. One is the average speed. And when we say the speed is constant, okay, what does it mean? That an object is traveling equal distances in equal time intervals. Okay, so we're going to be referring to only two speeds primarily, nothing else more than this. Okay, constant speed, which is equal distances in equal time intervals, average speed, which is total distance traveled upon the total time taken. So likewise, just as we see that the definition is primarily relating distance and time in ratio format, so the unit of speed is going to be meter per second, to be written scientifically as ms raised to -1. There could be speed that can be expressed in kilometers per hour as well. So we will just understand the conversion of it. That 1 kilometer per hour is equivalent to 1,000 meters over 3,600 seconds. 0 cancels, 2 5s are, 2 18s are. So this implies that 1 kilometer per hour is equal to 5 by 18 meters per second. Okay, just know this conversion. Likewise, if you want to convert meters per second to kilometers per hour, just reciprocal it. It will become 18 by 5 kilometer per hour. Okay, now as we see that speed is dependent on distance, which is a scalar quantity, time, which is neither scalar nor vector. I mean, it's scalar. So we therefore define speed to be a scalar quantity, which means it is again dependent only on the magnitude and the unit. Okay, no direction essential for uh, mentioning about the information of speed. Now, the idea is that speed can never always just be constant. It can be an increasing speed, it could be a decreasing speed. And in order to basically understand the nature of that, we need to understand motion graphs. So, as we know, speed is distance over time. So, we need to plot a graph of distance versus time. So, if I say that the distance isn't changing, even though the time is progressing, so we say that the speed is zero. Okay, because the object isn't changing its position. Likewise, if we say that with respect to time, okay, the distance is increasing const in a uniform way, we say that the speed is constant. Okay, so this is constant speed, where we are talking about equal distances in equal time intervals. And if I want to say that, okay, we are accelerating because the speed is constantly increasing, or I would say that the distance covered is unequal in equal time intervals. So this could be basically the increasing speed graph. Okay. And likewise, if it is slowing down, so the distance versus time graph is going to basically be like this. So basically, this is decreasing speed. So whenever speed is changing, we can say that we're accelerating or decelerating. So here the speed is increasing, so it is accelerating. Here the speed is decreasing, so it is decelerating. Okay. So these are four situations or scenarios under which we will be examined for sure. Okay. The only aspect here we see is that everything is in the first quadrant, which is in the positive quadrant, because both speed and distance are not direction dependent. So showing it them towards the negative side would not really make any sense to us. The whole idea is that if I have a distance versus time graph, and if we are referring to speed over here, what does that really mean? Okay, we need to understand how can we obtain speed from distance time graph. So whenever it's graphs, I guess we did discuss this in our first session, but if it's a graph, we need to use the intercept of the graph to extract information. So like if you see in the first scenario, if you're referring this to be the intercept, this gives me information about the starting or initial position of the object. So if I say, let's say this is 5 meters, so that's my starting position where I am right now at 0 seconds. Likewise, in the rest of the cases, it's at the origin. So it's at 0 meters only. And the second parameter that the graph can help us out with is the slope, which is also called as gradient. Now, the idea is very simple. We need to calculate it y2 minus y1 over x2 minus x1. So let's select two data points here. So this is going to be x1, x2, y2, y1. But primarily that's same as distance 2 minus distance 1 over time 2 minus time 1. And we know that distance over time is basically equal to speed. So this helps us to conclude that the slope of distance versus time graph, okay, the slope of distance versus time graph is equal to the speed of the object. Okay. Likewise, we have the third thing, which is area under the graph. But in this situation, area under the graph gives us no information, so we're not referring to that at the moment. Any question, boys, over here at this stage so far? Okay. Don't worry if you miss out writing anything very important. I will be sharing the OneNote link with you guys as well. So everything that I'm writing will be shared in exactly the same way. And the video is just there as a add-on for you to write it on. So if you feel that the classroom pace is going too fast, or if you need some time to write something, please stop me immediately. Okay, do not hesitate. So like this, what we're going to do is now we're going to tabulate information about distance, displacement, velocity, and speed. And then we will move on to the speed time graph section as well. Okay. So what we can do is we will prepare a table. So here I'm going to write information about just the term that I'm interested in. Okay. Here we'll write information about a possibility of a graph. Okay. And here we will write about what is the intercept of that graph represent. And then in the next column, we will mention about what does the slope of the graph represent. And the last case, we are going to write down what does area under the graph represent. It's a very interesting exercise because if you have this table, it's like more of a summary chart for you before the examination. Okay. So our first situation that we are taking here is we are taking distance versus time. Okay. So there are multiple possibilities of a graph, but we will just stick to one sample to just understand it. So we are taking distance on the y-axis, time on the x-axis, and let's say the graph is as follows. So here we're going to write information about the intercept. Here we'll write about slope, and here we'll write area under the graph. Okay. So if I take the intercept over here, the graph could be like this, could be like this. What it gives us information about is the initial or starting position. Slope will give us information about speed. Area under the graph gives us nothing. Okay. Likewise, Kabir, can you tell me if I have a displacement versus time graph? Okay. And the graph shape I stick down to is the same, like this one. Can you tell me what is the intercept giving us information about?
Is it distance from displacement from starting position?
But this is the starting position, right? See, origin is not the
Ah,
starting position. Okay. So for instance, I'm tracking your motion and I got a graph of your displacement versus type as the shape that's shown here, right? It means where did you start your motion from here, not from the origin, correct? So this is again same as starting position. Okay. What about the slope? Go on, Kabir, go on. What will the
uh,
slope of displacement versus time graph be?
uh, would it still be speed or velocity rather? Yeah.
The velocity here. And area under the graph is no information. Okay. So Arnav, now I'm going to be considering the speed versus time graph here. And I want you to answer what will the intercept give us information about if the y-axis is speed. The graph is somewhat like this. Yes.
The starting speed.
Okay. Initial speed. And what about the slope?
Acceleration.
Okay. Initial speed, acceleration, and area under the graph.
Nothing.
Pardon me, you need to be a little louder.
Nothing.
No information.
No information.
No, there is information. This is called distance. Okay. So let's try to understand this in a while. Okay. Okay, Abhinav, I'm now going to have velocity versus time graph. So tell me,
Sir, it'd be initial velocity,
that is correct.
and then sir, the slope would be acceleration.
Okay. Slope is acceleration. Okay. And what about area under the graph?
So would that be the change in the displacement?
Okay. So as of now, displacement is sufficient. Okay. And the last situation, it is acceleration versus time graph. The graph is as follows. Any one of you who would like to take the lead?
Sir, it would be initial acceleration.
Okay, it is initial acceleration.
So the slope doesn't give you anything,
Okay.
and then the area under curve would be the change in velocity.
Right. This is change in velocity. Okay. Now this consolidated table is extremely helpful before the examination. Okay. And it helps you to do a quick recap as well. Okay. We're going to be focusing on velocity versus time graph right now. Okay. And that will help us to do some derivation. Okay. And once we complete derivation of some equations, we will apply them into some questions as well. Okay. So our next topic that we're focusing right now is commonly known as kinematical equations. Okay. Or it is also known as SUVAT equations, or it is also known as equations of motion. So there are some conditions here that the motion has to be straight line, acceleration must be uniform or constant. Okay, and where there, which means that we're assuming that air resistance is negligible. Okay, that's a big assumption that we have to consider. That is a straight line motion, acceleration must be uniform or constant, and air resistance is negligible. Whereas in reality, we know that we cannot ignore air resistance, but the initial part of the discussion and concept is asking us to consider so. Okay, so we are going to be referring to the graph over here for velocity versus time. Okay, so as far as exams are concerned, derivation is not mandatory for you to know, but if you understand the derivation, you can solve graph-based questions relatively more easily. So the y-axis here is velocity, the x-axis here is time. Now the primary reason behind why we are considering velocity versus time only for the derivation, because if you can see in this chart, uh, it's only speed versus time or velocity versus time which gives us all the information, about speed, acceleration, distance, displacement. So you take intercept, slope, or area under the graph, everything can be extracted from these graphs here. Okay. So the graph shape, because we want the acceleration to be uniform, the expected graph shape has to be a straight line, okay, having a constant gradient here. Okay. And as we go ahead, so this is time 0. And from here, we have the time as time t. This is initial velocity u, and this is going to be the final velocity v. So why is it called as SUVAT? So first let's just write the meaning of it. So it's easier to understand the purpose. S is going to represent displacement. U is going to represent initial velocity. V will represent final velocity. Just like how we have alphabets U, V, so you can remember initial and final. A stands for acceleration and T stands for time. Okay, that's why it's called SUVAT equations. Displacement, initial velocity, final acceleration, and time. Okay. Now, just because it's a graph, we follow our fundamentals that the intercept of the graph, if we try finding out, is basically u, which is basically the information about the initial velocity of the object. So number one, done. Number two, if we go for the slope of the graph, okay, this coordinate here is t comma v. This coordinate here is 0 comma u. So slope is going to be y2 minus y1 over x2 minus x1, okay, which is apparently the same as that of v minus u over t minus 0, which is defined to be as acceleration. Okay, so if I rewrite this or rearrange this, it will become at is equal to v minus u. This implies that v is equal to u plus at. Okay, so that's your first SUVAT equation. So there is no specific order, okay, that this is number one, this is number two, this is number three. There are four SUVAT equations and you can remember them in any order that you want. Okay, so the slope of the graph is also done because we determine the slope for the entire line over here. Okay, so determine the slope basically for this portion. And the third one, area under the graph. Okay, now what does area under the graph here mean is that we are referring to basically this region here, this entire space, right? With respect to the x-axis, whatever space we have here, we're referring to this. Now, if you see, primarily this is forming the area of a trapezium, but I can also split this up into two parts by considering that this as area of a triangle and an area of a rectangle. Okay, so we stick around to that and we are going to consider that. So area under the graph can be two possibilities. That one, we know that area is equal to displacement, that we are already aware of because it's the velocity versus time graph. But I'll give you some more evidence of why it is displacement. Okay, so area is same as that of the area of trapezium. So Kabir, can you tell me what's the formula for area of trapezium?
It's a plus b over 2 times height.
Okay, so displacement here will become half into the sum of parallel sides. So we have two parallel sides here. One is u and the second is this entire length v. And this therefore forms the height, which is t. Okay, so this will become half into v plus u times t. This is your second SUVAT equation. So if you see, the speciality about the first one is that this equation is independent of s. It means if you don't have information about displacement, you should go for the first equation. The speciality of the second one is that it is independent of acceleration. So if you don't have information about acceleration, you can go for equation number 2. Okay. Now, why was the area same as that of displacement? Because what does v plus u mean? It is meters per second into time basically has a unit seconds. So if you cancel out, we are left with the unit only meter, which indicates that it's a unit of length. In this case, displacement because it's velocity into time. Okay. Likewise, we're going to derive one more equation for this by considering that displacement can also become in this case equal to area of a triangle plus area of rectangle. Now we see that following here very clearly. There's a rectangle formation taking place under the same area, and we have a triangle formation shape also taking place. Okay, so we can write the area of triangle as half into base into height plus this is length into breadth. So this is half into. As we see, the base is over here t, and the height is only this height over here. which is v minus u. The entire big length minus the small length, because this is u. Okay, so it's going to be base, which is t, into height, which is v minus u, plus length into breadth. The length over here is time, and the breadth is u. So it's going to be u into t. So this displacement is s. So this is s is equal to ut plus half into v minus u times t. Okay. But what do we already know? We know that v is equal to u plus at. And from here, we can therefore write v minus u is equal to at. We'll substitute this equation right up over here in place of this. So we'll therefore get s is equal to ut plus half at into t, which brings down the final equation as ut plus half at square. So this is your third Stewart equation, which is independent of the final velocity. So this is independent of final velocity v. So we see we have three equations here, 1, 2, 3, and each equation has something missing. But what's common is the value of u. All the equations need the initial velocity information in order to calculate this questions ahead. So we see that out of SUVAT, u is mandatory. Okay, so SUVAT, this is compulsory. Now we had one equation which is independent of S. We have one equation which is independent of acceleration. And we have one equation which is independent of V. Now we will design one equation where if you don't have information about time, we should still be able to solve it. Okay, so for that, what we're going to be doing is we're going to consider the equation V is equal to u plus at and S is equal to V plus u by 2 times t. This is the equation that we derived here, V plus u by 2 times t. Okay, so what we are going to do from here is, now we don't want time, so we have to think of eliminating the time in this equation here. So what we can write from here is V minus u is equal to at. So V minus u, the whole upon acceleration, is time t. We substitute that right here, due to which we therefore get S is equal to V plus u by 2 into V minus u by a, which is same as S is equal to V plus u times V minus u over 2a. On cross multiplying, we get it as 2as is equal to a plus b into a minus b, which is a square minus b square. So if you make v square the subject, we get u square plus 2as. Okay, so this is our fourth and the final Stewart equation. Now, what help do we have in the examination is that the examination provides you with a data booklet which has all the formulas, and they will clearly list down these equations for your usage. That they give you the freedom to refer to the formula in the data booklet. Okay, so where you have to develop your skill is in the application of it. So today, when we're going to be solving questions, we're going to be using these four equations, and using these four equations, we have to solve some different scenarios. Okay, we'll start with very low level of difficulty and then trying to move on a little bit advanced. Are we ready? Okay, give me a thumbs up if you guys are ready. Thanks, thanks. Okay, perfect. So let's begin. So we'll start with question number 2 here, and then we'll move on to the first one. Okay. Here the first question is, how far does a car travel in 45 seconds? So because this is the first question with me, just try to get the hang of the approach that we should be following, and then you can try the next two questions by yourself. So how far does a, yes, Abhinav.
Sir, after explaining the question, can you just go back to the formulas?
Oh, we can first finish this. That's okay. Okay. So now the question is asking here, how far does a car travel in 45 seconds if it has an acceleration of 0.32 meters per second squared? Assume it starts from rest. Okay. So what you have to do is you need to write always SUVAT. Now, how far meaning this is question. It starts from rest, so the initial velocity is 0 meters per second. We do not have information of final velocity. Acceleration is 0.32 meters per second square. The time taken is 45 seconds. Okay. So I believe you all have the equations written with you. Can you refer to them and tell me which equation should we use here to determine the value of S? Look at the equation that you guys have written and tell me which equation should we use here to find out the value of S.
So you can use ut plus half at square.
You need to give me full information. Okay. S is equal to ut plus half at squared. Right? So S is equal to 0 into 45 plus half into 0.32 into 45 squared. And from here, you will get, I guess, around 324 meters as your answer. I will just calculate it quickly. 45 times 45 times 0.32. Yeah, that's right. 324 meters. Got the hang? The approach has to be very, very simple, straightforward. Yep. Okay. This is still here. I want you guys to now try question number 1. Now here there are two things the question is asking me, time and final velocity, which means you cannot find final velocity first. You have to determine time without knowing the final velocity, and then you can find final velocity. The order has to be maintained. Come on, try.